last week of the term has begun. So what we will do in the rest of this course is to discuss further a little bit the character of the initial singularity. Last time I did the Bianchi-1 models for vacuum, which will play actually a more general and more interesting role as you might think in the beginning about a vacuum solution. These were the so-called Kastner solutions, and we have seen that generically they approach, the universe approaches initial singularity in a way that two spatial directions are shrunk and the third one is extended. That's what one calls a cigar singularity. So that's a generic case for the Kastner, for the vacuum Bianchi-1 matrix. Well, actually, we are interested in matter, not in vacuum. So today I want to discuss the Bianchi-1 models for a dust. And actually, this is considerably more complicated, and I hope I will manage to do the calculations. So let me see. So today we want to do the Bianchi-1 for dust. Well, what does Bianchi-1 mean? The metric has this structure. So we have, so to speak, three scale factors. Yeah, in Robertson-Walker universes, we have only one scale factor. There we have three scale factors, capital X, capital Y, and capital Z. So the three spatial directions expand in a different way. This is a flat metric, right? Spatially, this is for each time. This is just flat space. We have to allow for a factor here because there's a scaling of the spatial direction is time dependent. Yeah? At one particular time, we could rescale this so that this is just the ordinary Euclidean metric in 3 space, just by rescaling the axis. But this rescaling would involve the t, so we can do it only for one hypersurface, and then for the other ones, the t dependence would pop up again. But this is flat space which expands in different spatial directions in a different way. And with each of the scale factors, so to speak, the direction-dependent scale factors, we have kind of a Hubble parameter. So the one associated with x, we denoted A. The one we denoted with y, we denoted B. Yeah? This is, remember, A prime over A, this was the Hubble parameter. In the Robertson-Walker universe, this was the same for all directions. Here we have 3 Hubble parameters, so to speak. C is Z prime over Z. And then we introduced the symbol theta for the sum of all of them. Yeah, this is the expansion of the vector field perpendicular to the t surfaces. So we have here our hypersurfaces, t equal constant. Perpendicular to this, we have the vector field d by dt. This is a time-like vector field. And for those of you who are familiar with the decomposition of time-like vector fields into expansion, shear, and vorticity, this is just the expansion of this vector field. That's why it calls theta. Theta is the usual name for the expansion. But if you're not familiar with this decomposition, then it's just a definition derived from these 3 scale factors. So now we want to solve the field equation for dust. And for that, of course, we need again the Ricci tensor, which I had written already last time. I had calculated it just with the help of Mathematica. Minus a squared minus b squared minus c squared. That's the RTT component. Rxx was capital X squared over c squared a prime plus theta a. And then analogously for y and z, where I just have to replace x by y, a by b, and so on. So this is y squared over c squared b prime plus theta b, and rzz is z squared over c squared plus theta c. Okay, I try to distinguish the lowercase c, which is the speed of light, from the capital C, which is this parameter here, this Hubble parameter. And we will also need the Ricci scalar. I had written the result already last time, 2 over c squared theta prime plus a squared plus b squared plus c squared plus ab plus AC plus CA. That's it. And now, this time we want to do it for dust, not for vacuum. So for vacuum, we just had to set, and the mixed components are 0. Yeah, all the mixed components are 0. So I don't have to write them down. For the vacuum solutions, all these expressions were equal to 0, right? The vacuum field equation is just Ricci is equal to 0, but now we want to do a dust. So
just in one of the ACs and the less R equation for the Ricci scale, there should be an CB or
A squared, B squared, C squared, A, B, B, C. Yes, yes, thank you. Cyclic, right? A becomes B, B becomes C, B becomes C, C becomes A. Okay, so we want to do a dust. So we have an energy momentum tensor of this form, mu, u rho, u sigma. And we want to try it with a fluid velocity or a dust velocity which is perpendicular to the hypersurface, to the hypersurfaces. This doesn't always work, not for all Bianchi models. So there are, or to put it in a different way, there are Bianchi models where you have perfect fluid as a source, but the fluid velocity is not perpendicular to the hypersurfaces. That's what one calls a tilted Bianchi model. But here for the Bianchi one, actually it works with an untilted case, and that's what we want to calculate. So we want to have that the u with the upper index, the 4 velocity with the upper index is just the d by dt with the appropriate normalization factor. So this should be delta rho t. And what's the normalization factor? It should be normalized to minus c squared. Okay, that's it. Yeah, there's no factor. The factor is 1 because this is normalized to minus c squared according to this expression. And so I can write it in this way. And now if I pull the index, I need it with the index down. So this gives g sigma t, right? G sigma rho delta rho t is g sigma t. And g sigma t, there are no mixed terms. So the only term where this is non-zero is a gtt. So we have delta sigma t. And what is gtt? It's minus c squared. Minus c squared. That's a minus sign. Oops. Okay. So T rho sigma is mu, and this thing squared gives c to the 4. Minus sign squared gives plus 1. And then the two conicals, delta rho t, delta sigma t. Okay, and now the field equation. And we do it without a cosmological constant. So our field equation we want to solve is r mu nu minus r half, or let me write rho sigma. Rho sigma is kappa t rho sigma. So you see the mixed components are all 0. This has no mixed components, this has no mixed components, this has no mixed components. So we only have to consider the diagonal elements. So the t, tt, xx, yy, and the z component. Oops. So let me begin with the tt component. RTT is this here, minus theta prime minus a squared minus b squared minus c squared. That's RTT. Then minus r half times gtt. Gtt is minus c squared. So I have minus and another minus sign, c squared half times r. And r is this here. Begins with a 2 over c squared, which is very convenient. And then theta prime plus a squared plus b squared plus c squared plus AB plus BC plus CA. That's the left-hand side. Yeah? That's RTT, and that is, with a plus sign, that is minus R half GTT. And on the right-hand side, I have kappa GTT. GTT is mu c to the 4. That's the right-hand side. T, T, T. Capital T with indices little t. Okay, if I have done it correctly, then a lot of terms would cancel. Yes, this gives just the 1 here. Yeah, so this goes away. Then I have minus theta prime plus theta prime, minus a squared plus a squared, minus b squared plus b squared, minus c squared plus c squared. So we have just ab plus bc plus ca is kappa c to the 4 mu. That's our first component of the field equation. Let's call it E1. Then we have the xx component. Our xx is this here, capital X squared over c squared, a prime plus theta a. And now minus gxx times r half. Minus gxx minus gxx is minus x squared. X squared. And then r half. R half is where there's a 1 half in the field equation. And then from r I get 2 over c squared. 2 over c squared. And then this bracket here, theta prime is a squared plus b squared plus c squared plus ab plus bc plus ca. And on the right-hand side, I have txx. Txx is 0, yeah, because the energy momentum tensor has only a tt component. So, well, a little bit can be simplified. So this goes away, and then I divide by this. Of course, the scale factor is non-zero, otherwise the metric would be degenerate, right? So, yeah, that's it. I think I cannot do anything with this. Theta prime plus theta a minus c prime plus a squared plus b squared plus c squared plus ab plus bc plus ca is 0. And that's our second component of the field equation. Well, analogously, yy. I can do it just by cyclic permutation, right? So a becomes a b minus theta prime, and these 3 terms come again if I commute cyclically, and these 3 terms also come again. So this is E3, and quite analogously for the ZZ component. So I have c prime plus theta c minus theta prime plus the rest, as in the other terms, plus bc plus ca is 0. That's E4. So these are the 4 components of the field equation, the 4 non-trivial ones. The other one gives 0 equals 0, which is not much information. Okay, and now we want to solve this differential, the system of differential equation, right? So you see, it's a system of differential equations for A, B, and C, ordinary differential equations. Yeah, because of the symmetry, because of homogeneity, we have ordinary differential equations. Usually Einstein's field equation gives a system of partial differential equations, but because of the homogeneity, no x, y, z dependence, we have a system of ordinary differential equations. So, yeah, it's a system of ordinary differential equations for A, B, and C, because theta also is composed out of A, B, and C. And the way to solve this, the most convenient way, is first to solve a differential equation for theta. Yeah? So to deduce from the system of 4 equations an equation for theta alone. And that's not quite trivial. Let's see if I can manage to do this. So the goal is to get a differential equation for theta alone. Actually 1 order higher than the one which is on the board. Yeah, this is second order in the metric coefficients, right? It's first order in A, B, and C, But A, B, and C involve already first derivatives of the metric coefficient, so it's second order in the metric, as always. Einstein's equation should be. Okay, so we want to derive, this is a differential equation for theta alone, and I think it's a good idea to add these three equations together. If I add these three equations together, then I get A prime plus B prime plus C prime, which is theta prime. Then I get plus, okay, let me write it slowly, maybe not everyone sees it immediately. So these are these three terms added together. Then these three terms added together, A plus B plus C. This gives minus 3 times theta prime. And then I have this whole term 3 times, yeah? Plus 3a squared, plus 3b squared, plus 3c squared, plus 3ab, plus 3bc, plus ca is 0. Okay, but this here is theta prime. Yeah, a plus b plus c is theta. This is theta squared, because a plus b plus c is theta. And this can be written in the following way. Wait a minute, let me see, which expression do I? Yes. I write this in the way 3 theta squared minus something. 3 times theta squared gives this plus this plus this, and all these terms 6 times. Yeah, if I multiply, okay, or let me write it this way. A plus B plus C squared. If I multiply this out, then I get 3a squared. Fine, there it is. 3b squared, there it is. 3c squared, there it is. And then I get from the mixed term 6 times ab. I have it only 3 times, so I have to subtract 3ab. Yeah? Then I get 6 times bc. That's only 3 times, so I have to subtract it. And 3 times, and here I get 6 times AC, so I have to subtract it 3 times. So why is this nice? Because here I have theta prime, here I have theta squared, this is 3 times theta squared. Is the sign correct? Let me see. First of all, I forgot this one here, right? I forgot this one here, so let me write it here. So then I have minus 2, right? Minus 2, 3. Is the sign here incorrect? Let me see. Drawing. Boop, 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 boop.
Minus sign was in front of the bracket.
Here. Did I make it? Oh, yes. I think it's, yes. Yes, you see, here's a minus sign in front of the bracket, and I overlooked this minus sign. So all these terms have minus signs. Sorry for this. Yeah, there's a minus sign in front of everything. In all three equations, of course. Minus, 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 minus. Good. Then, of course, it's also here minus. Minus. And then here it's minus, and here it's plus. Okay. Hope now it's correct. Yeah, now it looks good. Yes. So this is plus 3 AB plus BC plus CA is 0. And with E1 is up there. This term here in the bracket is just kappa c to the 4 mu. So I have minus 2 theta prime, minus 2 theta squared, minus 3 plus 1, plus 3 times kappa c to the 4 mu is 0. That looks good. Oops! So we have, if I divide by minus 2, I have theta prime plus theta squared is 3/2 kappa c to the 4 mu. Let's call this E5. Okay, so we have at least eliminated the individual terms A, B, and C. We still have the mu in the game, which we don't know. So how could we get rid of the mu? Well, the idea is to take the as a derivative of this expression. So from this equation, oops, if I differentiate this, if I differentiate this, theta prime plus theta squared derivative, then I get, well, 3/2 kappa c to the 4 are of course constant. So we get a mu prime. Yeah. The density is a function of t alone, of course, because we have a homogeneous model. So mu can depend only on t, but it will depend on t. And, well, how can we evaluate this here? With the help of E1. So the strategy, I say it again, the strategy is to express everything in terms of theta alone. Yeah? And so we have to see if we can write this derivative in terms of theta. With the help of E1, we can write it as AB plus BC plus CA primed, which can be calculated with the product rule. So it is A prime B plus C plus B prime C plus A plus C prime A plus B, yeah? Just with the product rule. If I differentiate the first one, I get A prime B plus B prime A. The second one, B prime C plus C prime B. And the third one, A prime C times C prime A. Yeah?
Couldn't be the kappa c to the power of 4 disappear?
I'm sorry?
Shouldn't this kappa c to the power of 4 be gone when you insert the expression from E1?
What have I inserted? Let me see. E1. Oh, yes, you're right. Thank you. The 3/2 is still there, yeah? But this expression, this was AB plus BC plus CA. Yes, this is gone. Okay, and for A prime, B prime, and C prime, we have expressions, namely, these are our other components of the field equations, E1, E3, E4. So for a moment it will become a little bit long, but it will become short very soon. So A prime is, let me see, A prime is minus theta prime, no, it's theta A, sorry, minus theta A, minus theta prime. No, plus theta prime, I put it to the other side, right? I solve for A prime, so everything else is on the other side, and then plus A squared, plus B squared, plus C squared, plus AB, plus BC, plus CA, times B plus C. And then the next term, now I insert B prime. This gives minus theta B plus theta prime plus A squared plus B squared plus C squared plus AB plus BC plus CA times C plus A. And the last one, minus theta C plus theta prime plus A squared plus B squared plus C squared plus AB plus BC plus CA times A plus B. And the bracket closed. Okay, and now we combine terms which are underneath each other. So then we get what? I get a minus theta from these three first terms. And in the bracket, AB plus AC, AB plus BC plus BC plus CA, and then the same thing again. AC plus BA plus CB. So all these terms come twice. That's the first sum and multiplied with what is behind the bracket. And then the terms with theta prime. This is just 2 times B, 2 times A plus 2 times C. 2A plus 2B times 2C. And then this term here, again multiplied with the same thing. Plus A squared plus B squared plus C squared plus AB plus BA plus CA. And again multiplied with 2A plus 2B plus 2C. So this is, do I do anything with this? Let me check this. Oops. Yes, I think I do something with that. So I have 3/2 minus theta, and then 2AB plus 2BC plus 2CA. This is 2 times kappa C to the form U, yeah, with E1. So this is 2 times kappa C to the 4 U. That's the first term. Then I have plus 2 theta prime, and A plus B plus C is just theta. And here I have what? This is theta squared minus AB minus BC minus CA. Yeah, this is this bracket here. We have done this the same calculation already down there. Yeah, theta squared gives A squared plus B squared plus C squared plus 2AB, 2BC, 2CA. So I have to subtract these terms once. And this is 2 theta, right? 2 theta. And here I have again kappa. This is minus kappa C to the form U. So now it becomes pretty nice. So we have minus 2, minus 2, minus 4. Is that correct? Oh, let's see. Minus 4 kappa C to the form U. Plus 2 theta prime theta plus 2 theta cubed. And now we resubstitute for kappa C to the form U, what we have found down there. This is E5. Here. Kappa C to the form U is 2/3 theta prime plus theta squared. And if I combine everything, I have what? I have 3/2 minus 8/3. Yeah? Yeah? I forgot this theta. Yes, thank you. Oh no, let me do it this way. This 8 looks funny, but let me see. Let me see what we get. Minus 8, oh, yes, right. Minus 4. That's true. Minus 2 is minus 4, right? So it's minus 8/3. Theta times theta prime plus theta squared. And here I have plus 2 theta prime plus theta squared. Right? So this gives minus 4, and this gives plus 3. Oh yes, it's correct. It gives a minus 1. So it's minus theta prime plus theta squared. That's correct. That's correct. Very nice. Oops, that's our differential equation. Oops, for theta alone. Yeah? So we have reached our goal now. We have achieved our goal of deriving a differential equation for theta alone. And this can be solved. So let's solve it. So actually we can multiply it. Oh no, we leave it. We leave it as it is. So we solve this differential equation. Well, you have to play around a little bit with the equation to see how it works. And after a while, you find that the following ansatz will work with the ansatz. That you write theta in the form v prime over v with a new variable v, because then the differential equation becomes nice. So let me see. What do we get? Then we get theta prime is v double prime over v minus v prime over v squared and the v prime squared. Yeah, just with a product rule. And this means that theta prime plus theta squared is v double prime over v minus v prime squared over v squared plus v prime squared over v squared. So we are done. Yeah, that is theta prime plus theta squared. So the idea behind this ansatz is that this expression, which occurs in the differential equation, that this becomes very simple. It becomes then just proportional to the second derivative. So our differential equation, which was theta prime plus theta squared prime, is minus theta prime plus theta squared. So what comes out of this? So this is v prime over v double prime over v primed, minus theta is minus v prime over v, and theta prime plus theta squared is v double prime over v. If I multiply the right-hand side, the left-hand side out, I get v triple prime over v minus v double prime over v squared v prime. And on the right-hand side, I have minus v prime v double prime v squared. So as always, solving a differential equation relies on having a good idea how to do this. And here's a good idea with this ansatz, because now our differential equation is just v triple prime is 0. Yeah? I think I can solve this. So it means that it must be a second-order polynomial in the time, right? So it means that v of t is alpha t squared plus beta t plus gamma. So we have found our theta. Theta is then v prime. This is 2 alpha t plus beta over v, beta t plus gamma. And we have also found our mu, because look at the equation E5 down there. E5 sets as 3/2 kappa c squared, c to the 4. Mu is theta prime plus theta squared. Theta prime plus theta squared is v double prime over v. V double prime over v. So this is v double prime is 2 alpha divided by alpha t squared plus beta t plus gamma. Okay, now we are looking for dust solutions. So we are not interested in the case that mu is equal to 0, because this is vacuum, which we have done already. So alpha is not 0. Yeah? But if alpha is not 0, then we can divide numerator and denominator by alpha, and we can, which has the effect that alpha is set equal to 1. Yeah? Then we get new coefficients b over alpha, which is my new beta, b over alpha is my new beta, and gamma over alpha is my new gamma. So we get alpha equal to 1. So we have, let me write this down, what I've just said. So we want to have mu different from 0. This implies alpha is different from 0. And this means we can set alpha equal to 1 without loss of generality. Yeah, because then we can, alpha enters into the theta only in this way that, that we can divide by alpha above and below the line, and then we get the expression with alpha equal 1. If alpha would be 0, of course we would get something different, right? But this case is excluded. And then we have, the other thing is, we are free to shift the origin of our time axis. So we can shift the point t equals 0 to any time we like. Choose 0 of time such that beta is equal to 0. Yeah? So I can add a constant to my t so that I have in the numerator no additive term. And then my solution looks like that. Theta of t is what? Alpha is equal to 1, beta is equal to 0. So it's 2t over t squared minus plus gamma. And the density is, there was a 3/2 in front of it. 3 to the 4 mu. It's 2 alpha divided by the same thing, t squared plus gamma. Okay, so we have finished the first step. We have found our theta and also our density mu. We have not yet found the individual A, B, and C, and not the individual scale factors which derive from A, B, and C. So we now have to come back to the equations E2, E3, E4 in order to determine A, B, and C. There's a question?
Yeah. Didn't we set alpha equal to 1?
We set alpha equal to 1, thank you. Yes. That's it. Okay, so I think that's the next step. Let me look it up. Yes, that's it. Exactly. Now we solve E2. That's the differential equation for A. It's written here. So it's A prime plus theta A. Theta is this here. 2t over t squared plus gamma. And then we have, I write this again in the following form. Okay, let me write it as it is written here. Theta A, let me do it a little bit more slowly. And then I have here minus, not plus, minus, a squared plus b squared plus c squared minus ab minus bc minus ca. And this is theta squared plus ab plus bc plus ca. And this was 0. So that's it. So this here, a plus b, ab plus bc plus ca, was the density with a factor kappa c to the 4. Okay, and now let's insert our results for theta and mu. So we have a prime plus theta a. Theta a is 2t a t squared plus gamma minus theta squared minus 4 t squared. What do I do with that? Let me see. Do I want this? Oops. Sorry. First of all, I forgot a theta prime, right? Yes, I forgot a theta prime, and that's quite important. Excuse me. So here was a minus theta prime minus theta squared. And this is very nice, because minus theta prime minus theta squared is here minus v double prime over v. Yeah? So this is minus V double prime over V plus, let me write it again, kappa C for mu is 0. And now we can insert the expressions. A T squared plus gamma minus V double prime is minus 2T, right? If I differentiate this twice, I get I get minus 2T. No, minus 2, I differentiate twice. I get minus 2. And in the numerator I have, in the denominator I have T squared plus gamma. Yes, and kappa C to the 4 mu is 4/3. Here I have forgotten, no, I should point to this expression. Kappa C to the 4 mu is 4/3 T squared plus gamma is 0. Okay. So I multiply with T squared plus gamma A prime is 2TA, and put this to the other side. This gives 4/3 minus 2, is that true? 4/3 minus 6/3. This is on this side minus 2/3, so it's plus 2/3. Yeah, I think that's correct. Yes, it's correct. And now if you look carefully, you see that this is a derivative. What's on the right of the left-hand side is a derivative. It is T squared plus gamma A and the whole thing differentiated with respect to T. Yeah? If I differentiate the second term, I get this here. If I differentiate the first term, I get 2 times A. This is this here. So this is 2/3. And that's again a differential equation I can solve. Yeah, so this is T squared plus gamma times A is 2/3 T plus an integration constant, plus or minus. What is my notation? I think I write plus, and I call this integration constant P tilde. Yeah, that's an integration constant, P tilde. And so my solution is A of T is 2 times T plus P tilde divided by T squared plus gamma. And I forgot the 3, right? There's the 3. 2/3. And analogously, we get B and C. B of T is, well, this will be a different integration constant. Of course, the same gamma. The gamma is in the differential equation, but there will be a new integration constant, which I call Q tilde. 3 T squared plus gamma, and C of T is 2 T plus R tilde, another integration constant, T squared plus gamma. Okay. Yes, fine. So question is, are these 3 integration constants, P tilde, Q tilde, and R tilde, are they independent of each other? No, they are not. Because the sum of A, B, and C is theta, and we have a differential equation for theta. We have to see, actually, we have 2 equations for theta, actually. So we have to make sure that they are satisfied. First of all, the sum of these 3 things should be theta, and we know theta. Theta is here. Yeah. So that's the first condition we have to write down. Let me see if I get this here. So P tilde, Q tilde, and R tilde are related by 2 conditions. Well, remember what we have done last time when we considered the vacuum case, the Kästner solutions. We also had 3 coefficients, P, Q, and R, and we had 2 relations between them, the so-called Kästner relations. So we will get something similar now for P tilde, Q tilde, and r tilde. So again, we will have three parameters, three coefficients, which govern the time dependence in different spatial directions. But for the twiddled quantities, actually the relation will be different from the Kastner relations. So we have to calculate this now. So the first relation was that theta is a plus b plus c. So what was theta? We have determined theta. It's up there, 2t over t squared plus gamma. And now we have calculated a, b, and c, so we can add these three things together. So all of them have a 3t squared plus gamma in the denominator. And in the numerator, I have a 2. And then I have t plus t plus t is 3t. Plus p tilde, q tilde, r tilde. Oops. Okay, I have to get this up later again because we have to read the expressions again. So let me see. So this, of course, goes away, and the 2 goes away. And then I have t is t plus p tilde plus q tilde plus r tilde over 3. And this means p tilde plus q tilde plus r tilde is 1. It's 0, sorry, it's 0. It's 0. It was 1 in the Kastner case, but now it's 0. Yeah? Now it's 0. So it's not the Kastner relation for the twiddled quantities. This is the first relation. And then we had this expression for the density. What was it? This is E5 down there. 3/2 kappa c to the 4 mu was theta prime plus theta squared. So we have determined these expressions. Oops. Let me see. No, that's not the relation I want to use. This is true what I've written, but that's not what I want to use. I want to use actually E1. This expression. Kappa c to the 4 mu is, without the 3/2, is AB plus BC plus CA. That's the equation I want to use. So what is kappa c to the 4 mu? If I multiply with 2 over 3, I get 4 over 3 t squared plus gamma. That's a square. And on the right-hand side, AB plus BC plus CA. Let's see if I can arrange this in a way that we can see both boards. Oops. So I have to multiply this with that, this with this, and this with this, and add these three things together. So in the denominator, I have the denominator of a, b, and c squared. So I have 9 times t squared plus gamma squared. And in the numerator, I have the 2 squared. So I have a 4. And then I have what? I have this times this. This gives t squared plus tp squared, p tilde plus tq tilde plus p tilde times q tilde. So if I multiply the other two together, I get this another time, and from the third term another time, so I get this 3 times. And here I get each of the coefficients twice. And here I get Q tilde R tilde plus R tilde P tilde. Okay. So the 4 goes away. So I multiply with t squared, say with 9 t squared plus gamma squared. So then I get 3 t squared plus gamma. On the right hand side, the denominator is gone. So I have 3t squared plus 0, because p twiddle plus q twiddle plus r twiddle is 0. Yeah, plus what is written there? Plus pq qr plus rp. So you see the 3t squared goes away. And we have found that 3 gamma is p twiddle q twiddle plus q twiddle r twiddle plus r twiddle p twiddle. And what we have on the right hand side can be written in the following way. I can write this as p twiddle plus q twiddle plus r twiddle squared minus p twiddle, let me say 1/2 this, 1/2 this. Then it is minus 1/2 p twiddle squared plus q twiddle squared plus r twiddle squared. You see this? If you multiply this out, then you get the squared terms. So I've subtracted them again, so they are gone. And then you have the mixed terms, and the mixed terms are precisely what we have here. Yeah? 1/2 times 2 p twiddle q twiddle is this here, and for the other terms in exactly the same way. And why have I done this? Why have I rewritten this in this way? Because this here is 0. So we have found that minus 6 gamma is, or let me write this to the other side. We write p twiddle squared plus q twiddle squared plus r twiddle squared. This was, in the Kastner case, it was 1, right? But here it is minus 6 gamma. That's the second relation. So we have again 2 relations for our coefficients. One for the sum of the squares. So we have essentially only one parameter. Yeah, essentially there's only one parameter in the game, because we have 3 parameters which are related by 2 equations. And well, another interesting information comes from this equation. Because the squares cannot be negative, it means that gamma cannot be negative. So gamma is either 0 or it's positive. So let's check what happens if gamma is 0.
Vice versa.
I'm sorry?
Vice versa, I guess, because gamma cannot be positive otherwise.
What have I said?
You said gamma cannot be negative.
Sorry, of course. Gamma cannot be positive. Yeah? So it's either negative or 0. Let's assume what happened if it's 0. So, oops. So the case 1, let's say, gamma equals 0. Well, if gamma is equal to 0, then each of these coefficients must be 0. Yeah? Because they are squares, they cannot compensate each other. So this means that all 3 coefficients are 0. But if all 3 coefficients are 0, what happens with A, B, and C? Oops. They become equal. Oops, where are they? Yeah. Yeah. So if this is 0 and this is 0, then this is just 2 divided by 3t. This is also 2 divided by 3t, and this is also 2 divided by 3t. So then we have a of t is b of t, c of t is 2 over 3t. So that's an isotropic expansion. Yeah? All 3 spatial directions expand in the same way. So that's a Robertson-Walker universe. It's a Robertson-Walker universe. And we are solving the solutions for dust without a cosmological constant. So what is this? What is the metric? That's a good old friend. Dust solution without a cosmological constant and spatially flat. Yeah? The Bianchi models are spatially flat. Spatially flat, dust, cosmological constant equals 0. Come on, you should know this. No, you need a dust and a pressure if you want to mimic a cosmological constant, yeah? We have only a dust, we don't have a pressure. No, it's an ordinary dust solution. It's a solution which was considered already very early in history, before people thought about dark energy or things like that, so before they brought the cosmological constant again into the game. This was a metric which was favorized at the time when the people thought that there would not be a cosmological constant. It is a Robertson-Walker spacetime, but a particular one, yes. It is a Friedmann solution, yes, but a particular one. No, it's Einstein-de Sitter. Yeah, that's Einstein-de Sitter. Remember, we did the dust solutions with and without cosmological constant. And we had these three cases where we had either the recollapsing or for the three cases of little k. Not with, without a cosmological constant, but for the three cases of little k. Positively curved, not curved, and negatively curved. And we had either the thing which recollapsed, this was a cycloid, or the thing which goes up for infinity. And the borderline case was Einstein-de Sitter. This was k equals 0. So this goes to infinity, but it just arrives asymptotically with speed 0 at infinity. So this is Einstein-de Sitter here. And we know this already, so we don't have to discuss it again. So we exclude this case now. Yeah? So case 2, that's the case we are interested in, is gamma is different from 0. And this means that because it's with a minus sign, it's a sum of 3 squares, then we must have gamma strictly smaller than 0. So we can write gamma as minus some squared, which is positive, and let's call this ti squared, where ti is bigger than 0. Yeah? Actually, you can read from the expressions for theta, for instance, or yes, here from this expression, you can see that gamma must have the dimension of a time squared. Yeah? So if it's negative, it's reasonable to write it in this way. So this is, well, this will be the time. I stands for initial. Yeah, so it will be the time where the Big Bang takes place. Okay, then we have these two relations, and we can now solve the differential equations for x, y, and z. That's our final goal, right? We have now the a, b, and c. The a, b, and c, give us again differential equations for x, y, and z, and that's what we have to solve now. Let me see if I forgot something to say. Don't think so. And minus 6 is correct. Yes, minus 6. Okay, fine. So let's solve the. So we will now determine x, y, and z. So our differential equation is what? Where are we? Here. Here, x prime over x is a. X prime over x is a. So this means dx over x is a dt. And a was, where's a? Oops. A is here. A is 2 t plus t twiddle dt divided by, 3 times t squared plus gamma. 3 times t squared plus gamma, and this is minus ti squared. So you see already that, that something happens if t is equal to ti, right? Then you have a 0 in the denominator, which indicates that something interesting is going on. Well, and this is a differential. Well, this is of course a log, if I put the integral signs in front of this, and that's an elementary integral. Yeah? Linear function divided by quadratic function. Yeah, you can solve it with, what is this method? My goodness. Don't get the right word. word, something with fraction. How do you call this decomposition? Partial fraction decomposition, now I got it. Partial fraction decomposition. Or you look it up in Bronsted, and that's what I did. So the solution is, so here you get the log, yeah, and then you exponentiate everything, and the solution is x of t is t minus ti with an exponent p, not p twiddle, it's a new exponent which I call p, t plus ti, exponent 2/3 minus p. And the new exponent p is expressed in terms of the old one and the time ti by, it's 1/3 1 plus p twiddle over ti. Ti is non-zero, so we can divide by it. Yeah? That's the solution of this differential equation. And analogously, y of t is t minus ti with a new coefficient q, with a new exponent q, t plus ti 2/3 minus q, and q is related to q twiddle, of course, in the analogous way. And for z of t, we get t minus ti r, t plus ti 2/3 minus r, and r is this here with q twiddle replaced by r twiddle. Okay, that's the solution. Yeah, these are our metric coefficients. This gives us the metric. So there's an initial time ti involved, which must be positive. The construction is done in a way that it must be positive. And then we have three exponents, p, q, and r, which are related by two equations, because p twiddle, q twiddle, and r twiddle are related by three equations. And we will now write these two boxed equations in terms of the untwiddled exponents. And actually, we will see that they have precisely the same relations as the Kastner relations for the vacuum solutions. So these may be called again the Kastner exponents, p, q, and r. I should also write the mu, or let me see, we have it on the board still, I think. Here. This was this here, yeah? 3/2, or let me write the 3/2 to the other side. Let me write kappa c to the 4 mu is then 4/3. It was t squared plus gamma, and this is minus ti squared. So you see, if t is equal to ti, I have a 0 in the denominator, so the density becomes infinite. So this is, yeah, it's a singularity. So ti is positive. So if we have a oops, here our time axis, then we have here the 0, here we have ti, and here we have minus ti. And we see that we have, so to speak, two universes, two possible solutions found. One starts with a Big Bang at ti and goes to infinity. So this is one universe. And another one goes backwards from minus ti, so it has a big crunch at the time minus ti, and it starts at t equal minus infinity. So here we have a big crunch. And here we have a Big Bang. Yeah? And we cannot extend the solution beyond ti, or this one beyond minus ti, because then the mu goes through an infinity. Yeah? So whatever the signs of p, q, and r are, we will discuss them in a minute, it's always true that we have the singularity for the density at t equal plus ti and t equal minus ti. So we cannot go through this point. Yeah? So we are either here in this regime or we are in this regime. And of course we are interested in the right one, which begins with a Big Bang and then evolves to t equal infinity. That's the one we will be interested in. But mathematically the time the time reverse situation also exists. And what we still have to do is we have to find out how the P, Q, and R are related with each other. So the relation between P, Q, and R, and then we can discuss the behavior of the individual components X, Y, and Z. Yeah? Because the behavior of this expression depends on the sign of P. Yeah? So if P is positive, then this is expanding from the initial singularity, but if P is negative, then it becomes infinite at T equal Ti. And this we have to find out what possibilities exist for the three signs of P, Q, and R. So let me write what is P plus Q plus R. I have to add these three things together. So I get 1/3, and then 1 plus 1 plus 1 is 3, plus P twiddle plus Q twiddle plus R twiddle divided by Ti. But this was 0. This was 0. So this is 1 plus 0. So our first relation is P plus Q plus R is 1. Exactly the same as we know from the vacuum solution for the Kastner coefficients. And then we have to see what happens to the squares. P squared plus Q squared plus A squared. Oh, then I have to square these things and then add them up. So if I square the 1/3, I get a 1/9. And then I get, when I square this term, it begins with a 1. This also with a 1, this also with a 1. So I get 3. And then the mixed terms, this gives 2 P twiddle over Ti. And here is the same thing with Q twiddle and R twiddle instead of P. And then the last one, this squared plus this squared plus this squared gives P twiddle squared plus Q twiddle squared plus R twiddle squared over Ti squared. What is this? 3/9 is 1/3, right? This is 0. The middle term is 0, yeah, because the sum is 0. And the last term is where the sum is minus 6 gamma, but gamma is minus Ti squared. So it's plus 6Ti squared over Ti squared. There's no bracket. But a 9 in the denominator. Okay? So this is 1/3 plus 2/3. This is 1. Yeah? Ti squared, of course, cancels. So I have P squared plus Q squared plus R squared is 1. So what we discussed last term for the Kastner coefficients is also true for these coefficients. They satisfy exactly the same relations. And to remember what the geometrical interpretation was, so if we draw this in a PQR diagram, then we have, this is a plane. It's a plane through these 3 points where I have the unit vectors on the axis. Yeah? This is a triangle. And the plane spanned by this triangle, this is determined by this equation. And this means that I have to intersect this plane with a unit sphere. So what I get is a circle, the so-called Kastner circle, supposed to be a circle. Yeah, you have to you have to view it as in perspective. We look at it from under a certain angle. So it's elliptic in the if we project it to the plane, but it's a circle in space. Can you imagine this? So you take the plane, which is determined by these 3 points, and you intersect it with a unit sphere, and that's what you get. Yeah, and that's a so-called Kastner circle. So we have again a one-parameter family of solutions, also for the dust case. And yeah, the parameter is the parameter which runs around on this circle. And we know already what kind of solutions these two equations have. We have discussed last time the four possibilities: all three equal to 0, 2 equal to 0, 1 equal to 0, and all three different from 0. And some of the cases were possible, some were not. And we just have to recall these results now. And we can then discuss the behavior of these three coefficients. And actually that's the reason one of the reasons why I did the vacuum case first, because these results can be used now that we have found last time. So we have the four cases to discuss. To find out what are the possible signs of P, Q, and R. Oh yes, I think I can manage to finish this. Oops. Ah. Okay, so the four cases we have to distinguish. So we have four cases. So the first one is, well, just for completeness, let's assume all three of them are 0, but obviously we are in contradiction with both equations, so this is impossible. So at least one of them must be different from 0. Let's say the first one is different from 0, and the other two are equal to 0. Then the first equation in the box says that P must be equal to 1, right? So if the other two are 0, then P must be equal to 1. And let's see, what are the x, the y, and the z? Here they are. Oops. So the x is then, so P is equal to 1, t minus ti. And there I have an exponent 2/3 minus 1. That is minus 1/3. So I can write it in the denominator with an exponent plus 1/3. Yeah? That's the x. And the y, well, actually q and r are the same, so the y is the same as the z. And it's a thing with q equals 0, so something to the power 0 is 1. And this is 2/3 minus 0, so I have t plus ti to the power 2/3. And I look at the version which starts, it's a positive time part. So we have here 0, here ti, and here is the universe expanding. So if we approach ti from above we see that this goes to 0. This, nothing particular happens with the denominator, right? This is always different from 0 if we are in this regime. It becomes 0 here, but this is irrelevant if we are in this regime. So this is nice. The denominator is harmless. It's positive. But this becomes 0. And the other two stay finite. Yeah, they stay finite on the whole regime. The universe stops here. We cannot extend it beyond this point because this becomes 0. Yeah? So the metric degenerates. We cannot continue through this point. So this is a kind of singularity where one of the coordinates, we have chosen the x-coordinate, where one of them shrinks to 0 at the initial singularity, and the other two are finite. So that's what we call a pancake singularity. Yeah, and in the Kastner diagram, in this picture where we draw the circle, so you see we have the pancake here. This is p equal 1. Of course, it's analogously for q equal 1 and r equal 1. So here we have the pancakes. Pancake, here is a pancake, and here is a pancake. So this is something which did not exist for the vacuum case. For the vacuum case, we didn't have a pancake singularity. You remember what we got for the vacuum case in this situation where two of the Kastner coefficients were equal to 0? Remember this? We did it last time. You got Minkowski space. Oh, you have your notes, you looked it up. Yes, we got Minkowski space here for vacuum. So in the vacuum case, we have here at these three distinguished points, we have Minkowski space in the Rindler representation, which is actually a Bianchi 1 universe. And here we get something more interesting. If we have the dust, it's a true singularity, right? The density becomes infinite at t equal ti. So yeah, it's obvious, yeah, because the volume shrinks. Yeah, even if two dimensions remain finite, if the third one collapses, then the volume goes to 0. So the density, if the mass is finite, the density must go to infinity, and that's what happens. So this is, but the pancake is the exceptional case, yeah. So for all the Kastner solutions, it's a whole circle. We have only these three special points where we get a pancake, and then let me see the other two cases. We have 1 equal to 0. So let's say PQ is different from 0. Which means that P and Q are individually different from 0. And the third one is 0. So we checked this last time and we saw that it doesn't work. We don't get a solution. So this is impossible. And then the generic case is the case that all three are different from 0. And we have seen last time that the two Kastner relations, the two relations in the box, require that one of them must be negative and the other two positive. That's the only possibility. So we had, let's say, if P is the biggest one, then they may be equal. There's a special case where they are equal, but they both must be strictly positive, and the third one is strictly negative. What does that mean? This means that if we look again at x, y, and z, well, this is harmless. If P and Q are positive, this means if I come from positive times and approach Ti, that then the x and the y dimension shrink to 0. Yeah? Because if the exponents are positive, then this goes to 0 if Ti is approached from above. So the x and the y direction shrink to 0. But in the other direction, it goes to infinity. Yeah, because r is negative, I have the t minus ti in the denominator, so this goes to infinity. So the z direction is stretched, x and y is shrunk. And that's what we discussed already for the vacuum case. It's a vacuum behavior for the Bianchi 1 models, and this is a cigar singularity. So we have the cigar generically. Also for the, I should mention that these terms are harmless, yeah? Whatever the exponents are, these are always finite. They stay always finite, so they go neither to 0 nor to infinity. So if we expand them, if we do a Taylor expansion about t equal plus ti, then this begins with a constant term, a constant non-zero term, a constant strictly positive term, and this also, and this also. So it behaves in linear approximation like a constant coefficient. If this would be constant, then it would just be the vacuum Kastner case. So we see if we approach the singularity for the cigar case, the generic case, then the behavior is very similar. It's qualitatively the same as in the vacuum case. So it's a little bit surprising because the density becomes infinite. You would say, oh, the density will certainly play an important role. But nonetheless, for the qualitative behavior of the scale factors, the density very close to the singularity plays no role at all. Yeah, it's exactly as in vacuum. You have exactly the same behavior as in vacuum. And this is the generic case. So on these three arcs, we have the cigar singularity. Here is cigar, here is cigar. I'm afraid you cannot read anything in this picture, but I will produce a nice picture for the lecture notes so that you can see it more clearly. This is generic, yeah? So if you are not in these three particular points, then you have the cigar singularity. And that's what we wanted to learn from this calculation. So the Bianchi 1 models have the nice property that everything can be calculated explicitly. Calculation was a little bit long, it wasn't quite trivial, but actually, well, every individual step was quite simple, right? It was just a little bit involved to derive everything. But the remarkable thing is that it could be derived explicitly. There are not so many cases where we can solve Einstein's field equation exactly. And for the Bianchi 1 models, actually it works in a comparatively simple way. And we get this behavior for the dust. I only did it for dust. You can also do it for perfect fluid or for more complicated matter models. Actually, Bianchi 1 has been discussed with more or less any matter model you can imagine, because it's next to the Robertson-Walker case, it's the most simple case you can do. And well, the lesson to learn from this calculation is the singularity is still there, even if we drop isotropy. Yeah? You might have thought, well, if you have an isotropic universe and something contracts, then it will contract into a point singularity. Not very surprisingly. So you might think if you perturb the symmetry, then there will be no singularity anymore. But we still get a singularity. It has a different behavior, qualitatively different behavior, but the singularity is still there. And that's not only true for dust. You can also do it for a perfect fluid or for other matter models. As long as the matter model satisfies some reasonable assumptions, in particular an energy inequality, you would still have the singularity. The singularity cannot be avoided. And so we have exemplified this with the Bianchi 1 calculation. And in the last lecture on Friday, I will talk a little bit about results to the effect that this is really a generic property. And this is what goes around the work of the Russians, Belinsky, Kalatnikov, and Lifshitz, the BKL study of the singularity, and the singularity theorems of Hawking and Penrose. So I will summarize these results in a in a very, very quick run. So not doing any calculations, but trying to give you a flavor of these results. And what we have done today is actually, it's an example which illustrates these more general results with a particularly simple model. So the singularity is a very generic property of Einstein's field equation. Yeah? It's not an artifact of the symmetry or of oversimplifying idealizations. It's a very generic property of Einstein's theory. And what this means, this is still a matter of debate. Either it means our universe really started with this kind of singularity, or it means that we need a different theory in order to study the immediate neighborhood of the singularity.